is the first video for section 4.1 in AP Calculus, which is on extreme values of functions. So we're going to begin with basically some definitions of the various vocabulary terms that you're going to consider. Some of them are interchangeable with each other. A lot of them you should already be familiar with from previous math classes, but we're going to look at them through a new lens of what we know about calculus now. So to begin with, we're going to talk about absolute or global extreme values. So absolute extremes are going to be absolute maximums or absolute minimums. Those are going to be, an absolute maximum means that absolutely it is the highest y value that your function has anywhere in the entire domain of the function. An absolute minimum would mean that it is the absolute lowest y value that your function has anywhere on the entire domain of the function. Even if it's a closed interval, we can have absolute maximum and minimum values. And it's also possible to have two absolute maximums or more than one absolute maximum or absolute minimum if you have two x values that both have the same y value that happens to be the absolute max or the absolute min. You can read for yourself on the screen and note there the formal definition for absolute maximum and minimum. That's basically your generic explanation of what those things are. So then we have the extreme value theorem, which says that if f is continuous on a closed interval from a to b, then f has both the maximum value and the minimum value on the interval. So what that means is, for example, if I have a graph like this. Okay. Here, point A, and then here is point B. Now, we're only going to look at the interval from A to B. So we're only going to pay attention to this portion of the graph. So because it's a closed interval, if we looked at the entire graph, we would have said, yes, there's definitely an absolute maximum, and it occurs roughly right here. However, we would have said there is no absolute minimum, because we would assume that the graph continues downward forever, and so it would go all the way down to negative infinity. But since we now have a closed interval that starts at this y value and ends at this y value, this y value here, f of b, is the absolute lowest y value for that entire interval from A to B. So simply by knowing that it's a closed interval, that guarantees for any function, as long as that function is continuous on the interval, that you're going to have both an absolute maximum and an absolute minimum. Because it's possible that those absolute maxes or mins could occur at the end point of the interval there. Alright, another thing that we need to define is a critical point. So a critical point is a point in the interior of a domain of a function at which f prime equals 0 or f prime does not exist. Critical points are possible places where you could have maximums or minimums. They may be absolute maximums or minimums, or they may be relative or local maximums or minimums, and we'll define what those are in just a minute. So anywhere in the domain of a function where the derivative equals 0 or does not exist. So that's what you're going to be looking for when you're trying to algebraically find the places where a maximum or a minimum may occur for a function. So in summary, extreme values only occur at critical points and then at end points for the domain if the function is on a closed interval. If it's all real numbers for the domain, then we don't have any endpoints to worry about. So then you have relative or local extremes. They're still maxes or mins. It's just that they may not be the most maximum point for the entire graph or the most minimum point for the entire graph. For example, if I was to sketch a graph like this point right here would be an absolute maximum because it is absolutely the highest y value that the function ever has. However, this point right here is also a maximum. We would just call it a local or a relative max. And then this point down here, because it's a value like that, it is a minimum value, but because the graph continues down to negative infinity on both ends, this would be a local minimum. All three of those places I would be able to find using what we're going to learn about derivatives here in the rest of the video. So, and you can read for yourself on the screen or in your notes what those exact formal definitions are for relative extremes, but basically what I illustrated there for you on the graph should hopefully make that make sense to you. Also, you need to understand that an absolute extreme is also a local extreme, but a local is not necessarily an absolute. So, for example, going back to that picture, this point right here where I had the absolute maximum, it's also considered a local maximum because local to its area is the maximum. It just also happens to be the absolute maximum for the entire function. However, something like this local minimum here could not also be classified as an absolute minimum because it's not the absolute minimum y value for the entire function. So it does not work both ways. So absolute can be local, but local cannot be absolute necessarily. All right, so example 1, it says find the absolute max and min values for our function f of x equals x to the 2/3 on the closed interval from -2 to 3. So the first thing that you're going to do in this process is you're used to doing in your other math classes at this point. You probably graph that on your calculator and play around with the max and min. You have to do left bound and right bound and make a guess. And if there's multiples, it could take you 20 minutes just to do the one problem on your calculator. But one thing we've learned about calculus, you don't often have a calculator, and you're going to learn that you really don't need to do all of that mess on the graph anymore in order to do it. We can do it all algebraically using first derivatives. Okay, so we're going to find the first derivative. So this would be a power rule problem. I'll bring my power in front, and my new exponent would be -1/3. So another way that I could write that as 2 over 3x to the 1/3, or 2 over 3 times the cube root of x. It's going to be helpful down the road to have it written as that 2 over 3 times the cube root of x instead of as the x to the -1/3. So then the next thing you want to look for is where does that derivative equal 0, or where is it undefined? So to find where it equals 0, we would simply set the first derivative equal to 0. So to solve that, I would take the denominator, multiply it to the other side, and when I do that, all of this gets multiplied by 0, which means that I just end up with 2 equals 0, which can't happen. So that means that my derivative never equals 0. So the other thing that I have to look for in order to identify critical points is where is my first derivative undefined. So if you look at what type of function you get for your first derivative, that's going to lead you into determining where it would be undefined. When I look at my first derivative, I notice that it's a fraction. Fractions are going to be undefined, so it's a rational function essentially. They're going to be undefined anywhere that the denominator equals 0. So I'm going to set my denominator equals 0, divide by 3, cube both sides in order to get rid of that cube root, and so you get x equals 0. That means that I have a critical point at x equals 0. So now, when I get to step 3, which is to find the value of the function at each critical point and at your endpoint, and then label the points accordingly. So I'm going to find f of 0 because I identified x equals 0 as a critical point. However, since this is a closed interval, I also have to evaluate my function at the beginning and at the end of my closed interval. Notice I'm evaluating the function, not the derivative. I'm done with the derivative now. I used it in step 2 to identify my critical points, and now I'm done with it. So if we substitute -2 into our original function, we end up with -2 to the 2/3, which if we follow this formula, that would end up being the negative is irrelevant because we're squaring it, so it's the same as 2. to the 2/3, so you'd end up with the cube root of 4 there. Okay, and we'll just kind of leave it like that. Then we would have 0 to the 2/3, which is 0, and then we would have 3 to the 2/3, which is going to be the cube root of 9. So looking at these three, if we're wanting to identify the directions, we're to identify the absolute maximum and minimum. So that means of these three, one of these is the absolute lowest point of the graph, and one of these is the absolute highest point of the graph, and one of them is just it's a local max or min, but we don't need it for this problem because this problem is asking for absolute maximums or minimums. So we basically just need to compare the y values here. 0 is obviously going to be the smallest of all of these because the other two, cube root of 4 and cube root of 9, are both positive numbers. So that means that I have an absolute minimum at 0, 0. Now for the absolute maximum, you're probably not going to have a calculator for these problems because you could have just graphed it to answer it. So these are usually going to be no calculator problems. So as far as cube root of 4 and cube root of 9 goes, you don't have to know their exact values, but you just need to have an idea of which one's going to be bigger. Well, obviously, the larger number that you're cube rooting is going to give you a larger answer for the cube root. So that means that our absolute maximum is going to occur at 3, comma, cube root of 9. All right, so we're going to stop right there for this video. I know that there are more examples to come, but I don't want to run out of time or overwhelm you. So you can tune into the second video in order to see how to work example 2 and beyond.